Swayam Prabha. Digital India. Educated India.
Welcome. This is Vacuum Technology and Process Application course under NPTEL program, and we are going to the module number 2. In module number 2, we will be concentrating on production issues, production of vacuum, of ultra high vacuum, various ranges of vacuum. And before we venture into production, it is customary to revise certain keywords or concepts related to production, like pumping speed or throughput or ultimate vacuum or loading conditions. These are all related to production. Though in a way we discussed in the first module various concepts related to vacuum technology, it is necessary in a technical subject like this. Again we have to briefly mention the concepts related to production. As I was discussing earlier also, any technology, for example, whether electronics or nuclear or even food processing or chemical or pharma or metallurgy, it basically comprises 5 parts. That is, you have to produce something, and what you produce for quality control, you have to have certain measurements. Without measurement, whether your product is a high tech product or not, how do we know? So, second phase is measurement. Third phase is, with these measurements, with the products, you try to design some application. That time it will be called system design. You may have to bring certain other things from other places, other industries, but your products will be linked to those other products and to make a system design based on certain mathematical, physical and chemical fundamentals. Once you do the system design using necessary computer programming or MATLAB, etc., you try to really apply it in the world, real world problems. That is where a lot of engineering issues will come, particularly large scale industries. So, you will get lot of experience afterwards. Production, measurement, system design, when you try to really apply in an industry, in our case it will be vacuum industry, you will start getting a lot of experiences. Based on that, you may have to redesign and again reapply to get better product of the process. That product is not your product, you have produced, but based on that some general output will come, which is good for either national economy or public life. So, once you do that, it becomes a viable, reliable technology only when you are sure of repairing or troubleshooting. Otherwise, no technology is viable. Something goes wrong, there should be a way to repair it, like a fan. If small problems, if you do not repair, then fan cannot be a proven rugged technology. So, same thing here also in vacuum technology, particularly when you are applying for process applications, because this course is vacuum technology and process applications in a large scale. We have to have a good idea of all these aspects: production, measurement, system design, application and finally troubleshooting. And they are also interrelated, and there will be scientific issues, technological challenges, there will be industrial ideas, automation, controls, finally what you call troubleshooting. Then only you can use this technology in the public life. Okay. I am trying to give you a feel of importance of this production. That is the reason I am discussing these aspects, because production is the most important thing in vacuum technology. It basically deals with how do you produce vacuum in a small scale or large scale or very large scale or a continuous loading conditions, etc., etc. We will see that. Before that, it is customary to discuss the concepts of pumping speed and throughput. These two words come often again and again in production. Not only in production, when you do system design, when your early application is there, when you are trying to understand various parameters, how the process is going on, again we will come to these concepts, pumping speed and throughput. So, let us complete these concepts of throughput and pumping speed in today's lecture, which are related to production of vacuum. Well, the concepts that are going to be covered in this lecture are the concept of throughput, concept of pumping speed, and the relationship between these two, throughput and pumping speed. And based on these ideas, variety of pumps that are available in day to day world as of today, we will try to discuss in a simple way based on certain physical principles. That is under classification of vacuum pumps. So, once these four are understood, throughput and pumping speed and which pump to be used under the classification and what are the relationships, etc., the engineer will be in a position to design various pumps, various subsystems, various peripheral equipment and make a system, apply it and make it useful to the public. So, what is throughput? Throughput. In a vacuum system, what is throughput? In engineering, we normally talk of flow rate. It can be a volumetric flow rate. Sometimes with respect to systems, they will be called positive displacements, etc. Volumetric flow rate, dV by dt, or a mass flow rate when you multiply by the local density under those particular prevailing conditions. We are used to that in engineering, mass flow rate, but in vacuum technology, it will be little difficult to talk of mass flow rates, because your maximum pressure is atmosphere that is around us. We do not feel heavy mass on us, and as you are evacuating, it is still rarefied. So, it will be grams, milligrams, micrograms, nanograms, and in that nanograms or micrograms which are there within the container for a particular application like electronics or pharmaceutical or nuclear or space, and when you are trying to make them flow, it is all the more less, few nanograms per second type thing. You cannot make a measurement mass flow rates easily at such small levels, but luckily the science physics has taught us something. Pressure is proportional to what? Pressure is proportional to mass flow rate in a way. If more pressure is there, more density is there. Higher pressure for a small chamber, more molecules. So, per unit volume mass is more, so density is more. So, pressure is directly related to density. So, volumetric flow rate multiplied by density, you will see mass flow rate. So, in a way pressure can be related to density, through that it can be related to mass flow rate. So, whatever we do mass flow rate, we can also do in terms of pressure. dP by dt can be related to m dot popularly, that is dm by dt. We will see as time passes. So, that is the reason this throughput concept has been derived in vacuum technology. Mass flow rate is used in high pressures in engineering issues, whether it is thermodynamics or in IC engines or whatever, in engineering systems, mechanical systems. At low pressures, we talk about throughput, but it is proportional to mass flow rate. So, throughput is ideally defined as a product of prevailing pressure and the volumetric displacement. Throughput is volume of gas moving through a particular plane that we are observing, from left to right it is flowing, that is from chamber to the pump side. Per unit time, it is nothing but dV by dt when you look at a particular place, whether it is physically coming from the chamber which is being evacuated and it is going to the pump. And at various points there may be various pressures and there may be various densities, but at any plane if you multiply the pressure at that point and the volumetric flow rate dV by dt, that means product of P into dV by dt or P into V dot, it also represents rho into V dot, because P is proportional to rho. In fact, P in fundamental units in Boltzmann constant and temperature absolute, it can be also called P is equal to NKT, is it not? So, similarly here P into V dot is known as throughput. We have defined it so that it is somewhat measurable quantities. P you can measure, V dot you can measure from the pumping speed of it. So, with respect to chamber, throughput is nothing but something proportional to mass flow rate coming from system towards pump, P into V dot. It can be also considered as flow rate in moles, little bit more fundamentally when you are talking. It is what is gas is nothing but moles of gas. So, when gas is flowing, moles are flowing, that means dN by dt, that is n suffix m dot. PV is equal to nRT. So, PV dot by RT will become n dot, that many moles are flowing. In a macroscopic point of view, gas is flowing, and mass of gas in engineering systems, here throughput of gas is flowing. So, Q is P into V dot. We also know in n dot m is P into V dot by R naught T in a fundamental way. Now, manipulating these two equations, we can get another equation, that throughput is rate of molecular flow rate, that is flow rate in moles, multiplied by R naught T, that n dot m is nothing but m dot by molecular weight, m dot by m into R naught. So, finally, what I have been talking so far, we can see in the equation that throughput is proportional to m dot, because molecular weight is constant, R naught universal gas constant, T is the prevailing temperature. In a vacuum system, we will not think much of heat of compressions etc., because hardly any masses are being compressed. So, that way a constant temperature processes can be known. We will also see later at a different temperature, but even if there is a different temperature, the entire process will be at that temperature, that is also constant. When variable temperature type of situations will come very rarely, we will see during cryopumping or space simulation later. So, throughput I hope you have understood. What will be its unit? P into V dot, P will be torr and V dot will be liters per second. If you P can be expressed as atmosphere, P can be expressed as millibar, whatever you do. So, millibar into liters per second or atmosphere into meter cube per hour, one volumetric flow unit, one pressure unit. That is what I have given here. The unit is torr liter per second or millibar meter cube per hour, whatever particular unit system you are choosing convenient to that particular industry. So, same thing I have written here for your ready reference. Throughput is proportional to the mass flow rate at constant temperature. Further, pressure multiplied by volume has the same units of energy, because PV is nothing but energy, is it not? That is why in thermodynamics, those people who deal with thermodynamics, they know PV is basically energy. Consistent units you can also link them in terms of joules etc., through some constants. So, if PV represents energy, what PV dot represents? Rate of energy. So, that is power. So, from throughput, which is nothing but P into V dot, you can get a feel of powers involved. What do you mean by power in a vacuum system? It is the motor power finally, how much rate of energy is being spent to get this vacuum level. So, that way throughput is also important in understanding the type of energy input or power input required for that process. You can plan your startup industry that this much of energy I need to store or this much of power lines I have to make, etc. You can also think what will be a throughput and how much product rate is there in a particular application. So, everywhere you can utilize these concepts. Power is very important for us. So, this Q dot gives that. And when you look at the figure, that Q represents net flow rate coming from various sources, that we will see later. So, initially the chamber, process chamber, when you are evacuating, whatever gas is there inside that, that will be removed. After that, whatever is leaking, whatever is degassing, whatever is coming from various sources, etc., all that will be coming. Pump does not distinguish whether it is the gases are already available or something continuously coming. Something continuously coming is called loading, but whatever is being removed is pumped down. These concepts are very simple for us to understand, and that goes to the pump. This is called vacuum pump, and it can with a connecting pipe, and same throughput you can also link it through another equation called conductance into pressure drop P1 minus P2. How? Because whatever is flowing should be proportional to pressure drop. In mechanical engineering we know that. So, pressure drop multiplied by conductance is also throughput. Throughput, if you think electrical equivalent as a current, conductance is electrical conductance and pressure drop is like a potential drop. So, that makes sense. We will discuss little later in detail in terms of conductance, which is a function of the geometry of the pipe, etc. We will see later. Just I wanted to bring it here because when you discuss throughput, you should also discuss its relation to conductance, but conductance calculations in molecular flow, viscous flow, it is a big topic by itself. We have separately fixed a session for it, because that comes in just before vacuum system design. Then comes pumping speed. This is with respect to throughput, but pumping speed has another aspect which we need to understand in vacuum technology. A pump will continuously pump the gases coming from the chamber or loading or whatever leaks are coming through a interconnecting pipe, because you cannot directly connect pump and chamber, there will be interconnecting pipe. But with respect to pump, we are now discussing. In throughput means with respect to chamber, with respect to pump it is pumping speed, and at any pressure within the pump multiplied by the volumetric displacement of that pump, that is also throughput, that is P into dV by dt here also. So, that dV by dt is a characteristic of that pump, that V is different from dV by dt units here, and volume of chamber, that V is different. We have to be very careful initially, if necessary V1, V2 type of things. When you do system design, we will come to do that. So, this dV by dt is an internal structural aspect of the pump. Per unit time, how much of volumetric displacement the pump is doing, that at the existing prevailing pressure, that is called pumping speed of the pump, which is being used in evacuation process. S is equal to dV by dt V dot. Same concept now we are discussing from the pump point of view, and this pumping speed is a function of pressure. As pressure is going down, pumping speed also will come down. Ultimate vacuum, when you reach, pump is running, but vacuum is not improving. That means what? Volumetric displacement is not happening within the pump, so nothing flows from the chamber also. That way pressure reaches a constant thing, equilibrium pressure. So, that way also you can say pumping speed is a function of pressure. Pumping speed is not a conserved quantity, but throughput is a conserved quantity. Same thing is flowing from the chamber, same thing is flowing through the connecting pipe, same thing is flowing through the pump. Finally, it is getting exhausted. Throughout the cycle, what is being constant is throughput. So, pumping speed can be related to this throughput only when you multiply the existing prevailing pressure at the pump site. So, P into pumping speed S, that S is actually dV by dt related to pump. P into S is also throughput. At any interface between the chamber and the pump, at any plane, we are now talking about at that pressure and at that volumetric flow rate. Little later we will see with respect to chamber, total volume multiplied by dP by dt, V dP by dt is also throughput of that instantaneous time. So, all these things are related finally. So, with respect to pump, it is S is equal to dV by dt, and when you multiply with the pressure existing at the inlet of the pump, you will get throughput, because that what is there, that is same quantity of gas which is coming from the chamber. So, the relationship when you are talking between throughput and pumping speed, already you might have guessed that Q is equal to S into P, pumping speed into pressure. Okay. On one side we have throughput, which we have discussed, that is P into V dot, which is a conserved quantity right from the chamber through the connecting pipe up to the pump side, and from the pump side we have also discussed volumetric displacement of the pump, which is dV by dt, and these two are related by a fundamental equation in vacuum technology. Q is equal to S into P. Okay. When P is decreasing continuously, P is dynamic, and if S is constant, then also Q will be dynamically going down. Q may go down if S goes down. So, it is a product S into P, and units are matching. S unit is volumetric unit, volumetric flow rate type of unit, dV by dt. P unit is pressure unit. So, that is also millibar liter per second in the right side of the equation. Left side we already know that throughput is millibar liter per second. So, that way this apparently very simple maths, there is nothing great in this, but why I am stressing these points again and again are exactly on these points I have seen in my 35 courses in various industries, they get confused, because they purchase some pump, they think some loading is there in your chamber in a commercial application or a pharmaceutical application, how much vapor load is coming. Sir, what is load? That is also throughput. It is only a phrase, it is a sort of commercial word, loading. So, when you look at the figure, you will see there is a vacuum pump and there is a process chamber. That is our course, vacuum technology for process applications. So, during the process, gases have to be continuously removed by the pump. If there is a closed volume, what will happen? As pumping going on, pressure will come down. That way, volume of the chamber is always constant, V into dP by dt at that time we have to talk, that is also throughput. But in pharmaceutical applications, P will be constant, but still there will be continuous dV by dt going on from the process chamber to the pump. Though pump is running, pressure is not falling, because there is a continuous loading of the vapors coming to compensate on a continuous manner what is being removed. If either input stops or output stops, then pressure starts changing. So, if input stops, pump is running, then what will happen? Pressure will come down. Where output stops and input is on, then what will happen? Pressure will increase. Okay. So, we have to design the systems in such a way, whether we want throughput calculation at a particular process pressure, where that many liters per second we have to remove using the pump, that is loading applications, or we are only evacuating applications like bulb, TV tube or display systems or a space simulation chamber or a nuclear particle accelerator. There we are not interested in against load, there is no load much. Once you evacuate to 10 power minus 10 torr, this is so leak tight chamber, assuming that leak rate is not there, it is remaining at that vacuum. That remaining in that vacuum is important condition for that application. Unless you simulate that space condition, you cannot accelerate those particles. And few particles which are being accelerated, that is not a big load. A huge thousands of liters of volume which is there in a particle accelerator volume, few molecules, few ions which are being accelerated, there will not be pressure fluctuations. So, that is a constant pressure application, where the real problem is to evacuate thoroughly to realize nuclear fission fusion. But in a process applications like food processing or pharmaceutical, it is the other way. Continuously gases or vapors are coming, evaporated vapors from a fruit juice or continuously distillation column, continuously they are coming. But even though they are coming, pressure is not allowed to rise, that is why we need pumping. So, either way we have to understand the loads to the process and pumps matching to that, but in between connecting pipes come into picture, that I wanted to discuss later. In fact, suddenly with so much discussion on pumps and chambers, later in the third next session, I will suddenly tell you this interconnecting pipe, which is nothing but few hundreds of rupees, that is going to matter a lot, not the crores of rupees of equipment, not the crores of rupees of chamber, that is going to play an important role. That is called design. Even in CFD, what they do? The flow through a pipe, but pipe is not a costly thing, but process is very costly. So, that flow rate calculations and all we will see later in flow in vacuum systems, but flow fundamental relation is also connected to throughput. Throughput is also flow. So, different concepts are explained with different terminology at various instants of time in vacuum technology. We will repeat these concepts with different names later when you discuss process applications. There are quite a good amount of books explaining in fundamental physics, atomic level, all these aspects. 30-40 pages are there, kinetic theory, hundreds of pages they have written same thing. I am not going into detail, I am trying to explain in a simple English those concepts which are very fundamental, based on which all the technologies are now happening. So, this is what I want you to keep in mind. So, having understood all these things, throughput etc., before we venture into pumps, I will again discuss this slide later when we discuss individual pumps. Classification of vacuum pumps. Classification of vacuum pumps means on what basis we are classifying. There can be basis of low vacuum, high vacuum, ultra high vacuum. Low vacuum pumps like steam generator, water ring pumps or piston pumps etc., or rotary pumps or rotary piston pumps, high vacuum pumps like diffusion pumps and turbomolecular pumps, ultra high vacuum pumps like ion pumps and cryo pumps. But whatever is the pumping action, apart from application point of view, we can classify there also depending on the level of vacuum, but that is not important for us in engineering. What is the physical principle based on which they are classified? It is a gas displacement or gas transfer or kinetic energy transfer or gases retained in a chamber. There are various applications, we will discuss later in detail. Gas is continuously displaced coming from the process chamber through the connecting pipe into the pump and exhausted, and where you throw that is independent, that is positive displacement pumps. There are also pumps you take them, but you do not throw them out, pumps them, but keeps it with it. When you sweep the dust out of the house, that is positive displacement, dust is removed out of the house, but you sweep it to a corner, put it in a dustbin, dust has not gone out of the room, dust is very much in the room, but in a working environment it has gone, that is not positive displacement, it has not been displaced, but they are there. So, they are gas binding vacuum pumps, they are separately there, they are not interfering with the process of application in a nuclear or anything, they are not interfering. Like X-ray tube, there is a built-in pump, after 10 years vacuum should not be spoiled, then X-rays will not come out. So, there will be locally some pump which is eating those molecules slowly and continuously maintaining the vacuum, but that will not interfere your X-ray production conditions. So, that type of pumps are also there, where getter pumps are there, sublimation pumps, ion pumps, cryo pumps. You try to take the gases, condense them and keep it. They have not gone out, gases have become liquids and solids, there is no problem. Suppose I try to condense this nitrogen oxygen onto the walls like a cement, then vacuum is created. This is not positive displacement, this is absorbed into the walls. It is a retained gas binding on the pump itself. And when I want to remove it, I will give continuously momentum to that and try to remove, then it is called kinetic vacuum pumps. whereas I try to collect some gas, stop it, isolate it like IC engines, valve is closed type, then you try to compress it and exhaust valve is opened and you throw it. That means, there are 3 steps: collection, which is induction in vacuum, and then compression or sweeping first, then compression, exhausting. 4 processes will be there: suction, isolation, sweeping, compressing, exhausting. This type of things are called positive displacement pumps. We are not pushing the molecules physically and all, we are only taking the ensemble of molecules into a particular known chamber of volume, and that volumes are displaced, volumes are compressed, in such a way pressure rises finally at the exhaust and it is open. It is a simple thing only, you can easily understand when you read these books. I am not going to read this time, you can look into this table slowly, you will understand that. But all these aspects we will see again with the relevant pumps, and we will understand at that time whether it is a positive displacement pump or whether it is a kinetic vacuum pump or whether it is a gas binding pump. Broadly it is gas transfer and gas binding, but within the gas transfer we have positive displacement or kinetic principles. Within that there are varieties of pumps like steam jet ejectors or diaphragm pumps, diffusion pumps, turbomolecular pumps, rotary piston pumps, and finally rotary vane pump, which is very popular, which we are going to discuss very soon, scroll pumps, roots blowers. So many technologies have come over a period of time. Initially they were not coming as a part of vacuum technology. For example, Roots vacuum pump, Roots has made it as a Roots compressor, but today when you invert it, it has become a pump. And high speed turbines which are used in aeronautical application, they never thought that such a high speed can be used to produce ultra high vacuum here. Okay. A mechanical thing, a turbine rotating at very high speed for 60,000, 70,000 RPM, a fan rotates only hardly 1500 RPM. Such a beautiful bearings are developed, such high speed turbines are being developed. This technology has been converted as a pump in vacuum technology. So, vacuum technology has used other developing technologies like turbines and trying to make pumps out of it. Vacuum technology has also used cryogenic engineering and tried to make cryogenic pumps. Vacuum technology has also used steam jets etc. to make steam jet ejectors. Vacuum technology has used IC engine concepts or many other things like valving and compression, expansion. It has produced certain pumps like rotary piston, rotary in a rotating thing or a linear motion, rotary motion. Varieties of processes have gone into that, meant for various pumps. So, like every other technology, you have a variety of pumps based on variety of physical concepts. With this today's talk, what we have learnt is, we have understood the concept of mass flow rate proportional quantity called throughput. We have also understood the volumetric continuous displacement at the existing prevailing pressure with respect to pump, and this pumping speed liters per minute and throughput torr liter per second, how they are related by multiplying a local pressure, and that pressure multiplied volumetric flow rate is a conserved quantity. So, interrelationship between pumping speed, throughput, equilibrium pressures we have discussed, and their units also we have discussed. Later we have also understood what do you mean by loading, that means maintaining a vacuum level and continuous loading, or there is no loading excepting unavoidable leaks that are falling, which pump has to compensate. In a pump down time calculations, how much time it will take, that is also system design, we will see later. So, once we understand all these concepts, we are in a position to discuss one by one pumps. After pumps, we will try to discuss gauges. After that, we will try to discuss conductance pipes which are there between pumps and chambers. After that, we try to make a systems for metallurgical, material, mechanical applications, scientific applications, engineering applications, nuclear, space, computer applications. At the end, we will try to see the troubleshooting. So, I am closing this lecture with classification of vacuum pumps and fundamental concepts like pumping speed and throughput related to pumps. Thank you very much.